Let's take a look at the next related rates problem. For question number 3, the height of a triangle is increasing at a rate of 2 centimeters per second. All right, so the height is increasing at this rate, so I can write my related rates expression right away. So that's going to be dh divided by dt. So the height is increasing at a rate of 2 centimeters per second. And the base of the triangle is decreasing at a rate of 3 centimeters per second. Okay, so the base is decreasing. So that will be written as dB divided by dt. And that's going to equal to negative 3 centimeters per second. And I want to find out how fast is the area of the triangle changing. All right, so that's dA divided by dt. So how fast is the area of the triangle changing when the base is 8 centimeters and the area is 40 centimeters? Okay, so I need to figure out how fast is the area changing when I'm given these parameters. The base is equal to 8 and the area is equal to 40. Okay, so essentially I need to find dA over dt. So we're going to work with the area of the triangle. So the area of a triangle is area equals to 1/2 base times height. And if I want to find the derivative of area with respect to time, well, we essentially just take the derivative here. So this would be dA over dt. And then on the right hand side, we essentially use the product rule because I have a base and I have a height. So if I use the product rule, the derivative would be 1/2. And the derivative of base would be dB divided by dt times the height plus, and then I can treat this as one term there, so plus 1/2 times the base times the derivative of height, which is dH over dt. So there is my derivative using the product rule, and after that I just need to plug in the values that are given to me in the problem here. So let's go ahead and try our best to plug in the values here. So this is going to be 1/2. And let's take a look at dB over dt. That's essentially going to be negative 3 in this case. So this is going to be negative 3. And then I need then I don't know what the height is, so I'll label that as h plus 1/2. And the base right here, if I continue to read the problem here, the base is going to be 8. So 1/2 times 8. And then I have dH over dt, which is given to me at the beginning of the problem, which is 2 centimeters per squared. So this is going to be times 2 at the very for this last case. Okay. And the goal is I need to find dA by dt. Okay, so now the problem is I actually don't have my height here. So I need to take a look at this. I need to look at the beginning of the problem game where I need to find dA over dt when the base is 8 and the area is 40. And I still haven't used the area equals to 40 in this problem, and I'm going to use that to help find the height here. So if I take a look at my triangle, I know the area of a triangle is 1/2 base times height. And I want to find how fast the area is changing with respect to time when the area is 40. So when the area is 40, the base will be 8. And then with that, I can find out how high, or how I can find the height of the triangle given those parameters. And I can solve for h here. So 40 equals to 8 times 1/2 is going to be 4. So 4 times h. So that means my height is going to be 10. 40 divided by 4 is 10. And then from there I can take my 10 and I can plug it in for my h right there. So let's just do that right away. That's going to be 10. And then I have enough information to find dA over dt when the base is 8 and when the area is 40, and that means my height will be 10 in that case. If I go to my calculator and if I go ahead and calculate that, the final answer here would be -7 centimeters squared per second. All right, so the area of the triangle is decreasing at a rate of -7 centimeters squared per second. And just to kind of match up, the variables do match up. So time is on the denominator and area measured in centimeters squared is on your numerator. So that's how you would finish off that particular problem. Okay, let's move on to the next problem here. In question number 5 here, I have a spherical balloon here. So this spherical balloon is inflated with helium at a rate of 36 pi centimeters cubed per second. Okay, so as soon as I see centimeters cubed, I know I'm dealing with volume, so that's going to be dV divided by seconds, so that's going to be dt. So dV by dt is going to be 36 pi centimeters cubed per second. All right, so when we're given that, we should go ahead and write our derivative expression right away for dV over dt. And then I need to find the rate. So as soon as you read the word rate, I mean, that has to do with time there, of change in its surface area at the instant when the radius is 10. Okay, so I want to find the rate of its surface area. So I need to find dA over dt. And I want to find that when the radius is equal to 10 centimeters. Okay, so that's the information that's given to me. And since we're dealing with a sphere, there's two formulas for a sphere. There's the area of a sphere, and there's also the volume of a sphere. Okay, let's take a look at the area of a sphere. The area of a sphere is A equals to 4 pi r squared, and the volume of a sphere is equal to 4 divided by 3 times pi r cubed. So we're going to be using both of these formulas to figure out what's happening in this problem, because our main goal is I want to find the area. How fast is the area changing with respect to time when the radius is 10? Okay, so if I'm looking for dA over dt, I can start over here and I can take the derivative here. So this is dA over dt equals 2. And then using my power rule, 4 times 2 is going to be 8. And then the pi would remain. And then for this part right here, the radius, if I take its derivative, it's going to be dr by dt. Oh, sorry about that. I made a small mistake. The r would remain because I'm doing the power rule, and then I take the derivative of r, which is dr over dt. So I do apologize for that small mistake there. Okay, just by taking a look at this, I definitely know what radius is. The radius is going to be 10, but the problem is I don't know what dr over dt is. So I can't solve this problem without dr over dt. Alright, so I still haven't used my dV over dt, so what we're going to do now is we're going to work with our volume formula, and hopefully we can find something in there that can help us with this dr over dt expression right there. Okay, so let's go back to our volume of a sphere, and let's go ahead and take its derivative. It's dV over dt equals 2. Okay, let's use the power rule here. So 4/3 times 3 is going to be 4. So 4 pi r to the power of 2. So remember, using the power rule, the exponent decreases by 1 there. So 3 minus 1 is going to be 2. And then we need to use the chain rule here, and the derivative of r is going to be dr over dt. Okay. And let's go ahead and see if we can solve for this dr over dt, and once we do that, I can plug that in over here for my dA over dt expressions. Okay, so dV over dt, that's going to equal to 36 pi, so let's go ahead and plug that in. 36 pi equals to 4 pi, and then I have my radius squared, and the radius here is going to be 10, so that's going to be 10 squared times dr over dt. Okay, let's go ahead and eliminate the pi's here. And then 4 times 10 squared, that's going to be 400 dr over dt, and that's going to equal to 36. Okay, If I keep on isolating for dr over dt, that's going to be 36 divided by 400. And then I take my 36 divided by 400, if I reduce that, sorry, this didn't come out very nicely here. It's going to be dr over dt. 36 divided by 400 is going to be 9 over 100. And then I can plug that in over there, and then I can finish off the problem. All right, so this is going to be 8 pi. The radius is going to be 10. And dr over dt is going to be 9 divided by 100. And after that, I would just do your best to simplify this with a calculator, and the answer I get is 36 divided by 5 pi, and then centimeters squared per second. And just kind of match this up. Seconds matches up with time, and centimeters squared does match up with area. So 36 pi divided by 5 centimeters squared per second for that problem. Okay, let's move on to another related rates problem here. In this case, I have a cylinder problem. All right, so the height of a cylinder-shaped rubber tube has a volume of 24 pi centimeters squared. Now, just take a look at the units here. This is not a rate, that's just a volume. So the volume is going to be 240 pi centimeters cubed, and is stretched at a constant rate of 6 centimeters per minute. Okay, so we got to let's read the whole sentence again. The height is being stretched at a constant rate of 6 centimeters per minute. Okay, so since the height's being stretched out, that's going to be dh divided by dt, and the rate is going to be equal to 6 centimeters per minute. Okay, then the question tells you that the volume of the rubber tube does not change. Okay, so since the volume does not change, that means the rate that the volume is changing, dv over dt, equals to 0 because it's not changing, right? As it stretches vertically. Okay, and then I need to find the rate of the change in radius when the height is 15. Okay, so I need to find the change, or the rate and change in the radius, so that's dr over dt, and I need to find that when the height is equal to 15. Okay, so lots of information for this particular problem here, and since we're dealing with a cylinder here, and we're given dv over dt is 0, let's use the volume of a cylinder, which is volume equals to pi r squared h. And that's going to work out really nicely because I have an r variable. So if I have an r variable, when I take its derivative, I will have a dr by dt, which matches up with the information over here. And I also have an h, and if I take its derivative, that's going to be dh over dt. So that's going to help with that piece of information over here. Okay, so that's looking pretty good. Let's go ahead and find the derivative now. So the derivative with respect to t for volume is going to be dv over dt equals 2. And now we're going to use a product rule here. So in order to use the product rule, I need to use the power rule first. So that's going to be 2 pi r, and then the derivative of r is dr over dt times it by the h. All right, so we're using the product rule here, and then plus all of this will now stay the same. So that's going to be pi times r squared, and then the derivative of h is going to be dh over dt. So there is my product rule right there with respect to time, and from here on I'm just going to plug in the actual numerical values into my derivative expression here. Starting with this one, dv over dt is going to be 0, so that's going to be 0 equals to 2 pi, and then my radius will be r, and this is going to be dr over dt, and the height here in this case, well, if I read the problem here, the height is now going to be 15. Okay, so the height here is going to be 15 plus pi. Now I don't know what my radius is, so r squared, and dh over dt, this part right here, if I read the problem correctly, that's going to be 6 centimeters per minute, so that's going to be 6 right there. Okay, so I can't find dr over dt right now because the problem is I don't know what the value of the radius is. Alright, so we need to calculate the radius when the height equals to 15. And what's going to help us solve for the radius is that we know the volume of this cylinder is 240 pi centimeters cubed. Okay, so let's go ahead and figure out how that can help us here. We know the volume of a sphere is going to be pi r squared h. And I know the volume of the sphere is 240 pi. And that's going to equal to pi times r squared. And the height for this particular problem, remember, the height is simply going to be 15. So I'm going to multiply that by 15. All right, let's go ahead and solve for this now. Let's go ahead and solve for my radius here. The pi's can cancel off. And I now have 240 equals to r squared. And then I can divide both sides by 15. So divide that by 15. And if I do that, r squared would equal to 16, and that means my radius would equal to 4. Once I know my radius is 4, when the volume is 240 pi, I can take this 4 and plug it in here and there. Okay, so let's do that next. That's going to be 4, and that's going to be 4 to the power of 2. Okay, let's go ahead and just calculate all this out here now. Okay, so if I take 2 and if I multiply that by 4 and if I multiply that by 15, I get 120. And then the pi tags along, so 120 pi. And then I multiply that with dr over dt plus. Now, if I multiply 4 to the power 2, which is 16, 16 times 6 is going to be 96, so that's going to be 96 pi equals to 0. And remember, our goal is I want to solve for dr over dt. So let's just bring the 96 pi over now. So that's going to be negative 96 pi equals to 120 pi times dr over dt. The pi's can cancel, and that means dr over dt is equal to negative 96 divided by 120. And that's going to equal to negative 4 over 5 centimeters per minute. Okay, so the radius is decreasing at a rate of 4 over 5 centimeters per minute.